Privilege to introduce Professor Burgess. Actually, you wonder, I'm actually an experimentalist doing quantum transport, the one here. Actually, we started contacting Professor Burgess and Professor Dolan more than 10 years ago, and Jim Fong was in the audience, started this communication. That's why we have the honor of having him here. Professor Burgess did his PhD at the University of Texas in Austin with well-known professor, Nobel laureate Steve Weinberg, and he did some postdoc at Princeton for some time, and now he's a professor at McMaster and Perimeter Institute, Canada. And let's welcome Professor Burgess.
Can you hear me in the back? No? How's that? Yeah, that's better. Right, well, thank you for coming. My goal is to tell you about dark matter and dark energy, and it's a story I know that you've heard before. So I'd like to, and some, of course, here are going to be more experts than I am in some of these things. So, but I want to tell you the story, and of course, the Sherlock Holmes piece of it is I'm going to have some sort of an angle with Sherlock Holmes going through this thing, largely because it's a puzzle. It's probably the defining puzzle of particle physics and cosmology of our time. And that most of what's in the universe, we don't really know what it is. So, my message is going to be in several parts. And the story that you've certainly heard is that cosmology is having this wonderful time. They're testing the hot Big Bang model, or concordance cosmology, with unprecedented accuracy, and it's succeeding, and people are very happy. But what comes out of those measurements is that this pie chart of the universe, where for the first time in human thought, it's been possible to measure the energy density in the universe, regardless of whether you can see it or not. And there's this evidence that there's two kinds of things there. So the little pink wedge of atoms is everything that you ever learn about in university, which as physicists we can now bequeath that to the chemists, and then we get the rest of it, the green and the purple stuff, dark matter and dark energy, if we can figure out what it is. And so I want to give you an opinionated story here, and it's opinionated in two ways. I'm going to summarize the evidence for why there's things that we don't see. The first reaction everybody has when they see that pie chart is to say that, that successful story of cosmology you thought you had, you don't really have. If you really think that you can only make it work if there's not one but two things you don't understand, then you don't understand a lot. And so there's several things that I want to get across. One of them is that that's actually, although very natural, that's not the right reaction. And so there's a story there too. So why should you believe? What would it take to convince you that there's two kinds of new things that have never been seen? That would be part of the story. And then I want to, after giving you the evidence for why you should think those things are there, I want to give you my take on what they are. And for the dark matter side of the take, it's going to be not that unorthodox a take. And the dark energy side of the story, it'll be a little bit more unorthodox, in the sense that I'm going to give you what's not the majority opinion in the field. But there probably also won't be much time to go through the details of that, so you'll be spared a lot of what was not the orthodoxy of the field. Another attitude people often have when you see this story is you say that, well, you're inferring the existence of two things purely through how they gravitate, assuming that general relativity is the way that things gravitate. And wouldn't it be much more efficient to modify gravity and dispense with two new things and just have one new thing? And that would be some modification of gravity. And one of the pitches I will make is that the best evidence now, that may be what happens. And if that's what happens, more power to you if you're the person who finds out how that works. But right now, the best evidence I want to argue is that this is not what's happening. And I'll kind of get to why when we get there. And of course, if you're working on modified gravity, don't get put off by what I'm telling you. What I'm telling you is, I think, my assessment I think it's important that we explore all the options, but it's also important that every once in a while we sit down and say, well, so now, if you had to bet money, what would you bet now? And that's, of course, a time-dependent proposition. As you get more evidence, what you think is likely changes. And I'm going to give you my snapshot on what I think is happening now. So what would it take to convince you that there's stuff there that no one has seen? It's very similar to what was going on 100 years ago. You probably remember a couple of years ago, people were celebrating in 2005 the 100th anniversary of Einstein's big year in 1905. He wrote these 5 papers in that year. You know, the photoelectric effect was the one he got his Nobel Prize for. The Brownian motion one was the Brownian motion. No, that was actually what he got his Nobel Prize for, wasn't it? No. Brownian motion. No, there's something else I'm going to say about Brownian motion in a second. Yeah, photoelectric was the Nobel Prize. Special relativity you've all heard about. Mass energy was equals mc squared. Size of molecules, which I think was his thesis. And the interesting thing I found when I was finding out what these things were is that these two are the ones that were most cited at the time, the Brownian motion one and the size of molecules one. And the reason that they were most cited was that at the time people were not sure if atoms existed. And that was a very similar story to the story that I want to tell about dark matter and dark energy, that atoms were these things that no one's going to see or had seen, and when I was a boy I was told no one would ever see. Because, you know, of course, technology changes and now people write their names in atoms, but in those days, certainly, no one had any expectation of seeing atoms. And yet, right around right around the turn of the century, the 20th century, the consensus in science went from these atoms being some sort of a nice theoretical tool, but they're not really there, to a consensus that really atoms are there. And what convinced people at the time was that not one line of argument, it was that you had many, many converging lines of argument. You had many ways of estimating what the properties of atoms were and what their masses were and how many of them there were. And these were some of them, the Brownian motion story and the size of molecule story. And what was convincing was that they all gave you the same answer. If atoms didn't exist, these different lines of argument needn't have been related to one another and they needn't have given you the same estimate. But the fact that they all hung together and gave you the same answer told you two things. It told you partly that the whole picture of atoms was probably right, and it also told you what the properties of the atoms were. And so the burden on me will be to try and make the case for dark matter and dark energy in this way. It's not enough to have one line of evidence. You have to have many lines of evidence that all converge on the same kinds of properties. And that's what the cosmologists have been doing. They've been assembling redundant lines of evidence. So this is the way I'll lay it out. I'll kind of remind you of the background of the hot Big Bang for those that are not working on it. And then I'll go through the case for dark matter, which is the better case. It's been around since the 30s. There's 5 to 10 lines of evidence, depending how you count. And in there, I'll first tell you the lines of evidence, and then second, go through the flow chart of what the options might be to describe it. And that's where I'm going to sneer at modified gravity. And then the dark energy story will be similar. So here I'll go through. There has to be a case not only that something out there you can't see, but also that it's not the dark matter, which you also can't see. And then I'll make the pitch for dark energy as vacuum energy. And the main message there will be that the party line, if you ask anybody except for me on this in particle physics, would be that there is, unlike dark matter, there's no theories of dark energy which everybody could agree is at least a candidate theory. Normally the way things work is as soon as you have a problem like dark energy, there's 10 theories that could describe it, and you wait for the experimentalists to settle things. What's unusual about dark energy is that the consensus is that there's no theory that seems to describe the dark energy, and that's the problem. And so what's different between everyone else and me is that I think there's a solution. I think there is one solution, and that's probably the way nature works, given there's only one. And so so we'll see about that. But it's if I run out of time, it'll be that I won't tell you the solution. But that'll be the talk on Thursday. So come back. Okay. So what about the Big Bang? So I'm sure this is all a repeat for most of you. So what's the story with the Big Bang? And basically, the story of the Big Bang is that it starts off with Einstein. And of course, the Einstein story is that gravity is geometry. And for the solar system, that's the picture that you put some mass energy somewhere, it curves space, and then we're all just trying to get through life in the straightest arrow that we possibly can. And in curved space, that's just not necessarily very straight. And so we moved in these curved orbits, and those are what we call orbits. And that's great for the solar system, but it makes cosmology a science. If you're interested in what's the shape of the universe, or what's the universe, how has that shape changed in time, Einstein's connection between geometry and physics, and gravity in particular, is that it's now an experimental issue what the geometry of the universe is. And you can get at that experimentally in several ways. You can directly measure the geometry of the universe. Or you can measure where the energy is, and then Einstein will tell you what the geometry should be doing in response to that energy. And so it starts in the early 20th century because of that connection. And so you want to know where stuff is. And of course, what Einstein did is what you would do if you were the first person to have those tools. You'd say, well, let's assume that there's nothing special but us, and make this what they used to call the cosmological principle, that it's a very homogeneous space-time and it's a very isotropic space-time. But now, those are experimental facts. Turns out the universe is a very homogeneous place. This is a map of where galaxies are. This is from the Sloan Digital Sky Survey. And those are not pictures of the galaxies, but they're located where the galaxies would have been in this map. And so you see that they're kind of uniformly distributed. We're in the middle. There's fewer of them there just because the way they're looking for these galaxies is better at finding them farther away. It's not that there's fewer galaxies where we are. They're in wedges, not because the galaxies come in wedges, but because they're doing the survey in slices and they're not done yet. But what you get is that galaxies clump together, but if you go on large enough scales, they're pretty uniformly distributed. And so there's the odd thing, like on the left, you see the lines that are pointing to us. Those are called the fingers of God. Those are an artifact of how they search for these things. But on big scales, they're uniformly distributed. They're about to show you a whole bunch of a different class of galaxies that are easier that you can see farther away, and they're also even more uniformly distributed. And then if you go far enough away outside of all this to give you a sense of the scale of things, you get to this big blue sphere you're going to see in a second, which is the microwave background, and I'll say more about that in a second. But the basic story there is that if you look far enough away in the universe, eventually it becomes opaque, and you cannot see any farther. And that's been seen, and that's the blue thing. And you see these maps of the microwave background, and that's what you're looking at, is you're looking at the edge of the universe beyond which light doesn't propagate, as if the universe is transparent, for reasons I'll come back to. So that's what you're looking at. That's where stuff is. And so where is it going? That's captured by Hubbles Law. That the rule is that all but I think there's 10 or less galaxies that are moving towards us. All the rest of them are moving away from us. That's the first statement. Of all the billions and billions of galaxies that are out there. And apart from the nearest few, they're moving with this very specific law that the speed with which they recede from us, which is being plotted vertically, is linear in the distance they are from us, which is what's along the horizontal axis. And the constant proportionality is Hubble's constant. It's 70 kilometers per second per megaparsec. And that rule is there's a lot of nice things about that rule. But one nice thing about that rule is that if you were on the third galaxy over looking at all the other galaxies, if they're all receding from us with that particular rule, then you would see the same rule for your galaxy too. It's a kind of rule that everybody can share. If the rule had been the speed is the distance cubed or something, then that would have been special for us, and the other galaxies, you wouldn't have had the same rule. So that's kind of part of the story of the homogeneity of the universe is consistent with that rule. The second thing about that rule that's nice is that if the galaxies are not accelerating, and you run them backwards, they all get here at the same time, because the ones that are twice as far away are moving twice as fast, according to the rule. And that's kind of the beginnings of an explanation as to why that rule is true. If you had a bomb go off, the pieces will move away at different speeds. The ones that are moving faster will get farther. So if you look at where they are a little bit later, you won't be surprised to find that the ones that are farther away are moving faster, according to a rule like that. So that's the first piece of evidence that there was a Big Bang. The list of things on the left here are evidences that the universe is expanding. And I'm going to, every time I talk about evidence for something, like evidence for the Big Bang or evidence for dark matter, I'm going to, on the left, have a list of things. And I won't talk about them all. But part of my pitch is I'm supposed to tell you there's more than one line of evidence. And it's just, there's too many lines of evidence to be able to get through in a talk. But if you have questions, I can talk about these other ones. So the idea of these things, the lists on the left will be various lines of evidence for what I'm talking about at the time. And in this case, I'm talking about the expansion of the universe. So, what's the Big Bang? The observational evidence is stuff is homogeneously distributed around us, and it's expanding in a very particular way, in a way that's suggestive of an explosion. You might have said if there's an explosion, if we've been in a room in which there had been an explosion, the stupid way to figure that out is to look at how things are moving away from you. The smart way to find out if there's been an explosion in the room is to look for the hole, right? There should have been some damage somewhere. So you might have said that if there had been an explosion where the universe starts to expand, there should be a place somewhere which is not homogeneous. The universe shouldn't be homogeneous. It should look special. There should be where everybody receded from, that should be the place that looks, that should be the crater. It looks different from everything else. The fact that we don't see anything like that is evidence that it's not, the picture isn't that things are moving apart from one another in space away from some crater. It's that all of space is expanding. And so that when you run things back and everybody's here, all of space is here. And so there's no special spot in space, even though the universe is expanding like it exploded. So the hot Big Bang theory is just basically runs with that idea. It says that in the past, the universe was smaller. Smaller things would be hotter. And so it says that, well, let's take the simplest assumption that at some point things were so hot that everything that has any structure in it, including atoms and nuclei, have been knocked apart by the collisions involved in the heat. And let's say we have a soup of elementary particles, and we run that forward in time. Does that look like what we see, is the thought. And it was invented by people who did not believe the Big Bang theory. They didn't believe the picture of the expansion of the universe should have been from an initial explosion. And they made this assumption because they're trying to discredit the theory. And it just turns out that it gives a very good description of what we see. And so the tests that you hear about are tests of this specific model. And the way you test it is what I told you. How you test that picture is you look for relics of the earlier hotter time. Things like atoms couldn't survive when things were too hot. They couldn't survive because the collisions involved, what is heat? Heat is just the random motion of molecules. The hotter you are, the more energy there is in that random motion. So the collisions are more violent. So bound states will get knocked apart if they're colliding, things are colliding more violently than the energies with which they're bound. That doesn't mean they're not forming. It just means that as atoms form, they get knocked apart immediately. So what you expect to happen as the universe cools is that in the early universe, atoms were forming all the time, but they were getting knocked apart all the time. But as things cool, the collisions with which atoms find themselves having are no longer violent enough to knock things apart, and so the atoms that form stay formed. And that should be happening for every bound state we can think about, for atoms, for nuclei, for galaxies. And so you look for late time relics of that process, of the formation of things. And the two ones that are the main pieces of evidence for the Big Bang are the epoch where nuclei form, which is paradoxically the second one on that slide. When the universe was 10 billion degrees, protons and neutrons would have been able to bind together into nuclei. And then at about 1,000 degrees, those nuclei that had formed would have been able to bind together with electrons to form neutral atoms. And there's evidence that both those things have happened. And the earliest evidence we have that something happened is nuclei forming, the direct evidence. So what's that story? So I'm going to tell you the story of the nuclei first. And I have several agendas in this part of the story. And this is kind of many of you will know the story already, but this is kind of at face value, the reason I'm going to tell you the nucleus story in a little bit of detail here is that this is the poster child of an example of many lines of evidence all converging to tell you something. And what they converge to tell you is that there's a picture for how nuclei formed, which is very plausible, but it's also going to count the nuclei. So the success of this, our picture of how nuclei formed will tell us how many nuclei there were, and it will because the success of the story will be all about the competition between the expansion of the universe and how fast things are cooling, and the reaction rates that are forming nuclei as they collide with one another. And those rates depend on how many nuclei you have. If you have twice as many nuclei, it's twice as likely for one nucleus to find another one to collide with, and so you have more reactions happening. And so the success of our balancing of those rates to get the right abundance of nuclei is going to tell us how many nuclei there were. And part of my story, part of my agenda in a dark matter, dark energy talk will be to convince you that not only is it dark, it's not atoms. And so there has to be a way of counting the atoms which does not involve the way you're seeing the dark matter and the dark energy. And this is one of the ways you count the atoms. It's not the only way, but it's one of the ways you can count atoms without seeing them. And so part of the story here will be that the total number of atoms has been counted, and it cannot be what you would need to describe the dark matter and dark energy. So how does it go? So the story is the universe is cooling. As it cools, it is expanding, and as it expands, it cools. It starts off being just protons and neutrons and electrons running around. As it cools through the point where nuclei can form, they form. Or they were always forming, but they stopped getting broken apart. And then once things have cooled down and the universe has expanded much farther, the nuclei that have formed no longer can find each other anymore, so the reactions all stop, and whatever you formed in that time is what you get for nuclei later in life. And so this plot here is showing you a numerical simulation of what you should expect to see. What's being plotted here is, on this axis is the mass fraction of what's out there in various species of things on a log scale. So 0 is everything. The first tick is 10%, then 1%, and this is 10 to the minus 5, 10 to the minus 10. And this is time in seconds. So this is a few minutes. This is the origin of Weinberg's book. The first few minutes is about this story here of nucleosynthesis. The black line at the top is the number density of protons, and you see that almost everything's a proton because it's just below 0 there. And that doesn't really change much. There's always mostly protons out there. The next black line is the number of neutrons, and in early times that's essentially all you have. And then what happens is that neutrons take protons and they form deuterium, which is a proton and a neutron, and that's what this curve is. And as that happens, you get more and more and more of them. And eventually, as you get enough of this stuff, what happens is that they start to collide with other things. So the deuterium will collide with deuterium, and that'll give you helium, 2 protons and 2 neutrons, and that's the green thing, so that starts to happen. And then a deuterium can collide with a proton and a neutron, and that'll give you either helium-3 or tritium, and that's why these things start to grow. But eventually, as they get more and more of these things, they start to collide with stuff, and they make other nuclei, and so then you start to deplete some of them. So the deuterium you get eventually starts to, you're making enough helium from it that you start to lose the deuterium, and you turn it into helium. And so there's a period of kind of 100 seconds or so after the universe, after the Big Bang starts, where you're converting protons and neutrons into various kinds of nuclei. You've got protons, which are hydrogen. You've got helium-4. You've got deuterium. You've got helium-3. And there's various beryllium and lithium. You don't get things heavier than carbon because this stops too fast. But you do get the lightest nuclei. And after this, nothing much happens. And so what I want to do now is show you some plots that are like this. But what I'm going to show you is how much you end up with here at late times as a function of how many atoms there were in the universe. And so that's the thing that we're going to compare what you predict here as a function of the number of atoms in the universe with what's been measured as the abundance of these elements. So that looks like this. So here's, again, number density on a log scale. The top is everything. 10 to the minus 1 is the first tick. 10 to the minus 2 is the second tick. Here's the bottom. This is the density of baryons. So that's the density of protons and neutrons. And it's in a bizarre set of units where 1 means 10 to the minus 29 grams per cubic centimeter. And this is a tenth of that, and this is a hundredth of that, a thousandth of that. That number is not a random number. That's going to turn out to be the total energy density in the universe as we see it today. So if you thought that all that was out there was atoms, you should be expecting the answers here to be what you agree with experimentally. In this plot here, the horizontal faint pink line is the measured abundance of helium, the primordial abundance. It's about a 10% thing by number. And then the darker curve is the prediction. And you see that it kind of slowly climbs. It slowly climbs because the more you have, the more reactions you have. The more baryons you have, the more reactions you have, so the more helium you get. Helium is a very tightly bound nucleus, so the more reactions you have, the more helium you make, and then once you've got the helium, it stays there because it's very tightly bound. And you see that there's agreement for a wide range of numbers of stuff in the universe, but it's a very wide range because it's such a shallow curve that you're comparing to. That's the story for helium-4. Now what about helium-3? 2 protons and 1 neutron. Here's the theoretical curve. It's a falling curve now because the more baryons you have, the more reactions you have, the more helium-4 you make, but you made it from things like helium-3, so the less helium-3 you get, so that's why it's falling. And this is kind of the measured abundance of helium-3. And so they would agree for this kind of a range here. And here's the story for deuterium. Again, you're depleting it because it's making other things, and so it's a falling prediction, and here's the measured abundance, and they agree here. And here's the story for lithium-7. There's 2 different reactions, so there's kind of a funny theoretical curve, and then here's the measurement, and there's 2 colors because there's different kinds of uncertainties of measurements. But the important thing there is that if this is how nuclei are being formed in the early universe, they have to all agree for the same number of atoms. And they do. There's a choice for the number of atoms where those things all agree with each other. And this is an example of the redundancy argument. So this tells you several things. It tells you that probably this is how the nuclei did form. There's no reason, if nuclei were being formed in stars or some other place, why they should have to agree for the same number of baryons, but they do. And the more nuclei you have that do this, the more convincing it is. And second thing, it tells you how many baryons there are. There's this many, which is about 4% of what's going to turn out to be the total amount of stuff that's out there. So that's kind of it's a beautiful argument, and that seems to be the way the light elements were made. So that's the evidence that nuclei formed at one point. There's a similar story for atoms forming, but it's not exactly the same story. It's not like you count the different kinds of atoms that you could have gotten, because they all very quickly become ground state hydrogen. But the argument that tells us that actually atoms did form at one point is a different argument. And the way it works is it relies on the fact that the optical properties of the universe are different if it's full of atoms, which are electrically neutral, as opposed to nuclei and electrons, which are electrically charged. And the difference is very similar to the difference inside the sun. If you were in the center of the sun, it's hot enough in the center of the sun that the hydrogen in the sun is ionized, and so you really do have nuclei and protons and electrons running around. Whereas in the outer layers of the sun, it's cool enough that the electrons and nuclei have formed atoms. And so that part of the sun has different physical properties because it's made of atoms. And the important property for the present purposes is that the sun and the universe, when it's made of neutral atoms, is transparent. Because it's transparent because neutral atoms are not any good at scattering light. If you were in the middle of the sun where the hydrogen is ionized and you held your hand up in front of you, you wouldn't see it because the light would bounce around so much coming between your hand and your eye that the light you're getting at your eye has nothing to do with coming from your hand. It's not going in straight lines. It takes thousands of years for the light to get out of the sun because it's bouncing around so much in that part of the sun where it's made of ionized hydrogen. But if you're walking out of the sun, it would be very much like being in a cloud, because in a cloud it's the same kind of thing. Light is you can't see distances because light is scattering by the droplets in the cloud, but it would be a luminous cloud because there's a lot of light there. There's a source of light in the cloud, unlike in a cloud. So as you walk out of the sun, you're in this luminous cloud, and as you cross the line where it's now cold enough that atoms can form, what would happen would be very much like cloud lifting. It would become, you'd be able to see farther and farther and farther, and eventually you could see as far as you like because the sun would have become transparent. And so as you walk through that point, because it's luminous, there's a lot of light bouncing around. But after that point, the light that's there just keeps going in straight lines, and it escapes the sun eventually. So in the early universe, the same thing would have happened. That we would start off, the universe is so hot that the electrons and nuclei haven't found each other yet. They haven't formed stable atoms. The universe would be opaque. But as we cool through the point where atoms form, the universe would become transparent, and all the light that was there would still be here, but it's now moving in straight lines and not scattering anymore. And so you should be able to see that light, and that's what the microwave background is. It's the light that was bouncing around at the time that the universe became transparent. And now it's no longer, at that time it was optical, or it was similar to the kind of energies you would have when you're ionizing atoms. But it's since, as the universe expanded, been redshifted, so now it's microwaves. So that's the story. It was discovered in the 60s, and rather than showing you that slide, I found out recently that it was actually discovered in the 40s. So this is a piece in a book in 1950 by Hertzberg. It's a classic on spectra of molecules, and they had been measuring them in space recently. And they had two lines for a molecule that had been measured, and he makes the comment in the book in 1950 that from the relative intensity of these lines, you can infer the temperature that these molecules would have been in, and it's a temperature of 2.3 degrees. Turns out this microwave background has a temperature of 2.7 degrees, and that's why these lines have this property. But then he says, but which has, of course, only a very restricted meaning, because he had no idea why they should be at some temperature like 2 degrees. But in retrospect, they had seen the microwave background back then. But it was seen for real in the 60s in a story that I'm sure you've heard by people who were not looking for it. They were making microwave horns, and the way you test your horn is you point it at something which is not sending you microwaves and check that you're not seeing anything. And that was the sky, and they kept seeing something, and it turned out to be the microwave background. So now it's been measured very well. This is that map. This is the blue thing we were looking at in that movie I showed you earlier. And now you're on the inside looking out. And so this is the whole sphere unwrapped, the way you unwrap a globe. And what you're looking at here is the temperature of that hydrogen gas just as it formed, 100,000 years or so after the Big Bang. And so this is the hotter area, this is the colder area. What you can't see from this is the scale. The difference between the hotter and the whole thing is about 2.7 degrees Kelvin.